All right. Can everybody see chapter 20? Is it still loading or you got it there? Everybody can see chapter 20? If you haven't been taking notes while we do lecture, I might just want to remind you that a great way not only to participate in lecture is to comment when I ask questions or to, be following along. But another great way that you can actively participate in the lecture, learning new material, is by taking notes. And you don't have to write down everything someone says to take notes, but by taking information, processing it, and jotting down a little bit of information for you to recall later, that actually helps you remember things from lecture better than just watching the lecture alone. So note-taking is not just something that professors or, when you're in high school, people made you do. It actually is part of the learning process. So I don't know if some of you all print out these outlines or you just have the outlines and take notes as well. But whatever you do, if it's working for you, whatever your system is, that's fine. There's no way you can write down everything on these slides. So remember, they are available, but it is good to take notes. Does anybody take notes during the lectures or try to write some things down? I bet a lot of you do. Yes, all the time. Very good. I figured with as much success as we have in my Organic 2 classes that you all do things to be active learners. You've figured out that you want to be focused. Take notes when you rewatch. That's a good way too. I like that. That way you can pause it when you need to and write down things and spend time. I always would get my notes out and they were so sloppy. So I would take notes during class, but then I'd have to rewrite my notes, which was a good process too of reviewing them. But it was mainly not because I was so dedicated. It's because my handwriting was so horrible writing fast. All right. Well, let's get started. Chapter 20. Remember, we're in another carbonyl chapter. We gotta get happy about that. Woohoo! Carbonyls. Okay. The name of this chapter is carboxylic acids and their derivatives. Now, we did look at carboxylic acids in chapter 19 and some of their derivatives, but we looked at different aspects. We're going to look at reactions, nucleophilic acyl substitutions. So how carboxylic acids and their derivatives, some of the reactions that are nucleophilic acyl substitutions, and we'll talk about those. All right, so I had to figure out what picture I was going to put on this slide, and I thought at the very end of the chapter, your book does talk about lipoprotein particles and acylations of fatty acids, and how if you acylate a fatty acid, you can and it reacts with like a cholesterol. So an acylated fatty acid reacts with a cholesterol molecule, and you'll learn more about cholesterol, these ABCD rings, very common on steroids, when you get to biochem. But if you take the fatty acid, which had a carbonyl at the end, and you react it with acetyl-CoA. Acetyl-CoA is an acylating agent that forms a thioester of the fats in the cells. And once that thioester is formed, the thioester of the fatty acids can react with nucleophiles, certain nucleophiles. And so on cholesterol, there's an OH group. It's got a lone pair of electrons on that oxygen, remember? And we can do a nucleophilic acyl substitution between the thioester, that sulfur group is a leaving group, and the OH group, that's the nucleophile of the cholesterol, and they will form together this cholesterol ester. So you'll form an ester of the cholesterol by doing a nucleophilic acyl substitution. And this type of fat storage, called the cholesterol ester, is found a lot of times inside of these lipoprotein particles, right on the inside here. And they, as well as free cholesterol, form a lot of the plaque that's found in like arteries or blood cells, or arteries, I'm sorry. So I thought that was kind of an interesting thing at the end. And it's a nucleophilic acyl substitution and acylation reaction. And we'll be talking about that as we go. So that'll be at the end, something to look forward to there. So remember, is organic chemistry important? Yes, because if you are taking organic chemistry, you're probably interested in pharmaceuticals, medicinal chemistry, biochemistry, you know, anything that has a biological application, especially, has organic in it. So all that you're learning, you're going to see again. You're going to see in a different light, but you're going to see it again. All right, well, let's go ahead. I know this is a busy slide. We'll look at it piece by piece. And let's just remind ourselves about some of the functional groups that are considered carboxylic acid derivatives. What are some functional groups that are carboxylic acid derivatives? Well, in general, a carboxylic acid derivative has this type of structure. It has an acyl group. An acyl group is a carbonyl with an R group attached, okay? And attached to that carbonyl is not another R group, not another hydrogen. That would be aldehydes and ketones. It's a Z group. And these Z groups are more electronegative than carbon. They are things like oxygen, nitrogen, halogen, sulfur. So if we put a more electronegative atom onto a carbonyl, that is a carboxylic acid derivative, okay? So here are some examples of the derivatives in this box. Here's our functional groups that we'll be looking at in this chapter. The first, I think we all know very well, the carboxylic acid. It's a carbonyl with an OH group attached, right? Okay, so that's the carboxylic acid. We also have the acid chloride. The acid chloride is a carbonyl with the chlorine attached. Now, some people have asked, could you have other halogens attached? Yes, you could have a bromine attached. You could even have iodine or fluorine attached. I mean, those do exist, but the most common are the chlorides. So that's what we usually use, and it's not as reactive. So it's a nice stable reagent. We also have anhydrides. Have we seen anhydrides this semester? I think we've briefly seen them, right? An anhydride, not a lot. You are right, Catherine, not a lot. We will see them a little bit more in this chapter. An anhydride is a carboxylic acid derivative. Instead of an OH being attached to a carbonyl, think about an O carboxyl being attached with an R group being attached to a carbonyl. A carboxylate, for example, a carboxylate being attached to a carbonyl versus a hydroxide being attached. So that's an anhydride. Now, if you want to look at the anhydride just as a functional group instead of a Z, this is a carbonyl Z way of looking at it. If we look at it as purely a functional group, an anhydride has an sp3 oxygen that has two carbonyls bonded to either side. All right, so that is an anhydride. That one we haven't seen as much. All right, the next functional group that you probably have seen quite a bit is the ester. The ester is a carbonyl with an OR group attached. So instead of OH, we're going to have the OR group. We did talk a lot about amides as well. If you have an amide, you have a carbonyl with a nitrogen group attached to it. And so that nitrogen group can either have hydrogens on it, so it can be like an NH2, or it can be instead of hydrogens, you could have one or two R groups. So here's an example of a dialkylated nitrogen. But either way, as long as a nitrogen, an sp3 nitrogen, is attached to a carbonyl, you have an amide. All right, we're probably pretty familiar with most of those. Let's look at now classifying types of anhydrides, because that's one functional group, like you mentioned, we haven't seen a lot. So when we look at anhydrides, remember we're looking at them as carbonyl Z. This is our Z group, okay? That's how they're going to react. But if you look at the functional group more as an oxygen with two carbonyls attached to it, there are R groups on either side of those carbonyls. And if those R groups are the same, those two R groups attached to the carbonyl are the same, then we have a symmetric anhydride. It's symmetric anhydride. What do we call if the R groups are different? If the R groups are different on the carbonyls, like here's an R, that's a benzene. Here's an R prime, a methyl. So if the R groups are different, we call that a mixed anhydride. A mixed anhydride. And then finally, some anhydrides are cyclic. The oxygen that's bound to the carbonyl, instead of being bound to two different R groups, it's attached to a ring. And so they are cyclically attached. So in the back here, like here's an example of a simple one. Here's an anhydride where the two R groups are bound together in back. But we could start putting other things on those two R groups. So we could, you know, put another ring on or something. But if the anhydride is attached to itself in a cyclic way, we just call that a cyclic anhydride. So we've seen those too. All right. Let's see here. So those are the types of anhydrides: symmetric, mixed, and cyclic. Those are different ways that you'll see those. Let's talk about types of amides, because I mentioned those. Amides, the only thing that's going to be different in an amide are the type or what is attached to the nitrogen. So if we have two hydrogens attached to the nitrogen, which means that the nitrogen's only attached to one carbon, the carbon of the carbonyl, then that is called a primary amide. So a primary amide is primary because the nitrogen is bound to one carbon. So if you're bound to one carbon, you're primary. If we substitute out one of those hydrogens for an R group, then we'll have the carbon of the carbonyl plus the carbon of the R group. So if we have a nitrogen that's monoalkylated, that is considered a secondary amide because it's bound to two carbons. And then finally, if we are attached to a carbonyl, but then we have two R groups on our nitrogen, which is two different carbons attached as well. Now that nitrogen is bound to three carbons, we have a tertiary amide. You can only have amides that are either primary, secondary, or tertiary. Remember, nitrogen gets 3 bonds, okay? If you have 4 bonds to nitrogen, we'll talk about this a little later because there's a lone pair on nitrogen. If there is a 4th bond on nitrogen, that is called an ammonium salt. Okay, so you would have a cation. It would no longer be an amide. So we would not refer to that as an amide. So you can only have primary, secondary, or tertiary amides. Okay, all right. Now we're going to get into some interesting things in this chapter. Okay, on top of the fact that we learned about esters, we know what an ester is. It's a carbonyl with an OR group attached. So an oxygen and another R group. Just like we could have cyclic, like for example, our anhydrides, we said that our anhydrides could be cyclic. The anhydrides that are cyclic, the two R groups are somehow bound back to one another and we form a ring. The same thing is going to be true with esters. If the R group on the carbonyl side of the ester is linked back to the R group on the oxygen side of the ester, then we'd have a cyclic ester at that point. Cyclic esters are not called cyclic esters. They have a new name. It's a new functional group, kind of. It's a type of ester, but it's called a lactone. Has anybody ever heard of a lactone before? Maybe in a bio class? Usually you don't see lactones until you get a little bit higher, like in biochemistry. Usually you've had organic first, but sometimes you've heard of them. You just, haven't learned about them yet. All right, well, let's define a lactone. A lactone is really just a cyclic ester. A cyclic ester. All right, now let's look at some examples. These are 2 examples of lactones. We see we have a carbonyl. There's an R group on one side, and that we've got an oxygen with an R group on the other side, but notice those R groups attach. So it is a cyclic ester. Yes, that is. Yes, very good, Lauren. Yes. You're going to see a lot of lactones in medicine because a lot of compounds are kind of more stable in their ring state. But then once they get in acidic or basic environments, like inside of your body, a lot of those medications, the cyclic ring can open up. It does a ring opening reaction, and that's when it becomes activated. So yeah, in the medications, you will see those a lot. Very good. All right. When we look at lactones, cyclic esters, you've got the carbonyl OR group, but it's attached back to the other R groups. There's going to be two different types that you're going to see most commonly. We know that in chemistry, especially organic, 5 and 6 membered rings are most common. So that's also going to be true for the lactones. A 5-membered ring lactone is usually called a gamma lactone. And if you have a small screen, I'm going to redraw the gamma, but I'm not good with my Greek. No, I can barely write, regular alphabet, but that is a gamma. All right, the gamma sign, and it's a Greek word, a Greek letter. We've talked about how in organic, a lot of bioorganic, especially when we count carbons instead of counting 1, 2, 3. Once we get into carbonyl chemistry, we count carbons using the Greek alphabet, alpha, beta, gamma, delta, epsilon, and so forth. So what does it mean to be a gamma lactone? It doesn't actually mean that you have a 5-membered ring lactone. It means that on the alpha carbon to the carbonyl, okay, that's the alpha carbon, that means the first carbon over. If you keep counting alpha from the carbonyl side, alpha, beta, gamma, there are 3 carbons before we attach back to the oxygen of the carbon that reattaches to the carbonyl. So the gamma lactone means that the gamma carbon is attached to the oxygen connecting back to the carbonyl. It's that gamma carbon. Okay, so if you start here and you count around in Greek alphabet, alpha, beta, gamma, that's where we connect back. All right. And that's usually a 5-membered ring lactone. Now, a delta lactone has 1 more carbon in it, alpha, beta, gamma, delta. So this will be a 6-membered ring lactone. So if we start on the carbonyl side and you count your carbons directly attached to those, like the first carbon over from the carbonyl is alpha, and the second carbon over is beta, third over is gamma, fourth over is delta. Delta is the carbon that attaches back to the oxygen of that lactone ester. So this is a delta lactone. Okay. Those are going to be the most common, so that's why we're learning those. A delta lactone. Okay. Another functional group that we're going to learn, besides the ones up in the main box, is a cyclic amide. So a cyclic amide. Amides also have R groups on the Z group attached to the carbonyl. So if those R groups on one side of the carbonyl and the R group on the amide attach back, at least one of them. Hello, Claudia. That is okay. I'm glad you're here. I know you're usually on time, so I knew you'd come in. But if the R groups connect back to one another, now we have a cyclic amide. And we don't call them cyclic amides. They have a new functional group name. They are called lactams. So a lactam is a cyclic amide. Okay. The carbonyl R group attaches to the nitrogen R group. So here's an example. Now, the ones that we're going to discuss in this chapter, because a lot of lactams that you're going to see, yes, in antibiotics, yes, like penicillin or derivatives of that. Very good. A lot of those are going to be they're your active sites on the antibiotic where it ring opens. So the lactams that we're going to look at, a lot of them are going to be beta because of, like the antibiotics that we're going to talk about. And so from the carbonyl, if you go 2 carbons over, alpha carbon, beta carbon, that attaches back to the nitrogen of the amide. So we call that a beta lactam. There's 2 carbons there. And then if we have 3 carbon chain between our carbonyl and our nitrogen, 3 carbons is alpha, beta, gamma, then we can also have our gamma lactams. But, you can use the Greek alphabet and you can count the number of carbons. If the ring would be like 6, it would be a delta lactam. But these are the ones we're going to see in this chapter, just as examples. For example, you can also have a beta lactam or a beta lactone. We didn't talk about a beta lactone, but what does that mean to be a beta lactone? How many carbons are between the carbonyl and the oxygen in that cyclic species? It'd be 2, right? So if I had a beta lactone, here would be my alpha, and here would be my beta carbon. So it'd be that 4-membered ring. Yes, 2. Very good. So we've got a few new functional groups names to add to our lists. Just when you thought organic 1 was over in that list of 20 functional groups that we learned, maybe it wasn't 20, but you see that we keep learning new functional groups, like hemiacetals and acetals and imides, and imines and enamines. And now we're learning lactones and lactams. There's so many different functional groups in organic chemistry. All right, so these are the types of compounds that we're going to be seeing in this chapter. Carboxylic acid derivatives. What do they all have in common? What they have in common, just to remind you again, is they have an electronegative atom attached to the acyl group. So that's a polar bond. Okay. All right. Why are they lactones on esters? A lactone is the specific name for a cyclic ester. So if you have an ester, usually that's an open chain. The 2 R groups aren't attached. When the 2 R groups are connected to one another, we call that a lactone. It just has a new name. All right. Yeah. Same thing with the lactams. It's a cyclic version of the amide. All right. So what kind of reactions are we going to see in this chapter? We've seen them a little bit before, but we're going to just see more examples of them. So we're going to look at nucleophilic acyl substitution reactions. And this is where our Z group on any of those derivatives is going to be substituted by a nucleophile. So I'm going to be generic here, and I'm going to draw my carbonyl with my Z group. Okay. Now your Z group is your leaving group. It's more electronegative than carbon. And if we react with a nucleophile, okay, if we react with a nucleophile, then the Z group and nucleophile replace. There we go. Now I left some room here because instead of reacting with a negative nucleophile, that's our good nucleophiles, we could also react, which is a strong base, okay? Remember, strong nucleophiles are usually strong bases as well, okay? We could react with a neutral nucleophile. And if we react with a neutral nucleophile, then the reaction, a lot of times in this chapter, it will still occur, okay? But now we are going to have to deprotonate before the nucleophile substitutes or after the nucleophile substitutes. But either way, the product we get out will still look very similar. But now we'll have a protonated leaving group. And so it will be neutral. Do you see the difference there? The nucleophile is still switching with Z, but now look at the byproduct. Instead of Z minus, it's HZ. Just by switching those. They switch in either case. So why do we call this nucleophilic acyl substitution? Because we're doing a substitution reaction on an acyl group. Okay, now that acyl group there, it could be anything. I guess I'll put an R there. Let's put an R there. And what is substituting on the acyl group is the nucleophile. So that's why we call it a nucleophilic acyl substitution. All right. There's something we need to talk about with the Z group. The Z group that will be bonded to our carbonyl, because it's a more electronegative atom, I'm going to add this in a different color. The Z group has at least one lone pair of electrons. It could have two lone pair of electrons. It could have three. Okay, I'm going to go back a slide real quick and show you this, okay? One thing that you noticed about the acyl group with the Z group attached, I didn't mention this before, but all of the more electronegative atoms than carbon have at least one lone pair. So that's why there's a lone pair shown there on that Z particle. So if you look at examples, like a carboxylic acid, oxygen has two lone pairs. The acid chloride, chlorine has three lone pairs. The anhydride leaving group, okay, I'm showing you the leaving groups, the Z groups here, that oxygen has a lone pair. It has two. The ester, the nitrogen, they all have at least one lone pair of electrons. Now, that lone pair of electrons is next door to a carbonyl. So the carbonyl exhibits resonance with the Z group and its lone pair of electrons. Okay, so we can draw different resonance structures. If we take the carbonyl and we open the carbonyl up, we know that anytime you have a carbonyl, the minor resonance structure of that is the polarized carbonyl. So if we open up this carbonyl down here and put that pi bond, remember resonance is the movement of lone pairs and pi electron pairs. We don't break sigma bonds. But if we move that pi pair of electrons up toward the more electronegative atom, right, oxygen, then we have a plus minus. This is a minor resonance structure, the Zwitter ion. Okay. Now, from that Zwitter ion, we could stabilize this compound. Carbon does not have a full octet here. The Z atom next door, whatever that atom is that has a lone pair, can push its electrons in. Now carbon has a full octet on that carbonyl because we're donating a pair of electrons to it. Now this is also a Zwitter ion structure. We've got a negative charge and a positive charge here. It's not our major structure because it's charged. Our major structure is the version of these compounds that we saw on this slide. Okay, they are the best resonance structures. But oh, somehow all my notifications got turned back on my iPad. Boo! It must have done a reset. Do y'all ever have that experience? You turn off all your notifications and they start coming back on? All right. So I would consider this the major, this is the major resonance structure. But we do see, a minor resonance structure here where the lone pair next to the Z atom is donating electrons in, forming this Zwitter ion toward electronegative oxygen. Okay. So here's what the hybrid looks like there. I'm going to call this very minor because it's not a good resonance structure because first of all, it's got charge separation, but then also it doesn't fill all the octets. But what we see is that if we combine these three models, we see where charge is present in this polar molecule. Okay, a carbonyl with a Z group attached, whatever that Z group is a polar molecule, and there's partial charges there. Oxygen, it has a partial negative charge because if you look at all of the resonance structures, oxygen's either neutral or in these two instances, it's always negative. So that means it has a total partial negative charge overall between neutral and negative. If you look at the carbonyl carbon, this one right here, it's neutral, and here it's positive, and here it's neutral again. So neutral and positive, it's a partially positive carbon. That's our partially positive carbonyl carbon. And then the Z atom, what is its charge? Yeah, it's electronegative through inductive withdrawal. So it might be partially negative through inductive withdrawal, but the resonance shows us that it's also, because it's got a lone pair of electrons next to that carbonyl, it's also a donor, and it's partially positive due to resonance. Okay, so we've got inductive withdrawal making that Z atom more electronegative versus resonance donation making it electropositive. Okay. Now, if you're donating electron density as a Z atom, what you're really saying is that you're a basic atom. Bases donate electrons. Isn't that how we, all the way back in Gen Chem, if you're a Lewis base, you're an electron donor. Z is donating electron density, so it's considered basic. It's able to donate electron density. Z is a resonance donor. We call that a basic atom. One thing we'll see, especially as we go forward here, is that the more basic our Z atom is, the more able it is to donate electron density through resonance, okay, the more that resonance structure 3 contributes to the hybrid. The more that 3 contributes to the hybrid. So if Z is an oxygen versus a nitrogen, for instance, one thing you learned a long time ago is, like, if you looked at, let's just go back to water versus ammonia. Do y'all remember which one's a better base? Is water a better base, or is nitrogen a better base? Which one's a weak base that you learned in Gen Chem? Is it the water or the ammonia? Water is a very weak base. It's amphoteric. It can act as an acid or a base, but nitrogen was a better base. Do you remember that ammonia was the one that you learned was a weak base all the way back in Gen Chem? And then in organic, we said amines are weak bases, like in when we were looking at extractions. So while water can be basic, anything with a pair of electrons can be basic. Nitrogen's a better base because it's less electronegative. So it doesn't hold on to its electrons more tightly. If you're less electronegative, you can donate your electron density better because you're not holding on to those electrons. So for example, if we have on Z, if it's an oxygen, if it's an oxygen versus a nitrogen, nitrogen is a better base. So it's going to be, it's not as electronegative. It's able to donate its electron density better. And that means that this structure is more prevalent in the amide. And this structure is less prevalent when you have an oxygen on, let's say, an anhydride or a carboxylic acid, because oxygen is not as much of a donor. Now, if we look at this structure, let's look at structure 3. The more resonance donating Z is, the more that this is a major structure. It becomes a more major structure. In this structure, carbon is neutral. In this structure, carbon is positive. Let's say that we have a nitrogen attached versus an oxygen. If nitrogen's attached to our carbonyl, that nitrogen's more able to donate its electron pair in. Resonance structure 3 here will be more prevalent. So this carbon in your hybrid will be less positive because that is the neutral form of carbon. It's less positive carbon, right? Now, if we have something like oxygen next door, oxygen's not as good of an electron donor. So this will be a less prevalent structure, which means this will be a more prevalent structure. When oxygen is your Z group, there's a greater partial positive charge on that carbonyl carbon. Does that make sense? We'll go to the next slide and see if it does. Okay, so what are the basicity patterns of our Z atoms? I'm going to go all the way back. Remember our first slide, we had all those different types of Z groups. Like if the Z group was a chlorine, you were an acid chloride. If the Z group was a carboxylate, you were an anhydride. So put a carbonyl next to all of these electronegative atoms. Remember this? That was the acid chloride. This was the anhydride, right? All right, so if we take the Z groups and we look at their basicity, it turns out that there were 2 things we looked at to determine stability of a base. Actually, there were more, but I'm going to go off of a few first. We talked about the element effect. Do you remember when we were talking about acids and bases in Organic 1? We talked about the element effect of a base and how to stabilize. In the element effect, we said that bigger atoms were more stable. If you're comparing the same charge of an atom, and we're going to call that atom a base, something that can donate electron density, a bigger atom was more stable. More stable means a weaker base. Okay, now, out of all of these atoms, let's look at the Z atom attached. We've got a chlorine, an oxygen, an oxygen, an oxygen, and a nitrogen. Okay, now if we look on our periodic table, think about your periodic table in your head, CNOx. Okay, this is, I always draw by 7. Kind of looks like the state of Florida. There we go. But if we look here, nitrogen and oxygen are found in the second period of the periodic table. Remember, hydrogen's in the first period. Chlorine is found in the third period, which makes it a larger atom. The larger the atom is, the more it stabilizes the anion of the base charge. So because chlorine is a larger atom, it's going to be more stable than oxygens or nitrogens. That means it's going to be the weakest base. Okay? The bigger you are, the weaker the base you are. So chlorine is our weakest base. It's our weakest electron donor next to the carbonyl. Okay? That means that the nitrogen, well, we'll get to those later. But these are all stronger bases. Okay, now the second thing we looked at was electronegativity. The more electronegative an atom was, the more tightly it held its electron density. And if you hold your electron density in, you're a more stable base. That means you're a weaker base. So which is more electronegative? Is an oxygen more electronegative or a nitrogen? Remember your CNOx. Which one's more electronegative? Oxygen's more electronegative. So oxygen is a weaker base than nitrogen, okay? Because it's holding its electron density in, and if you hold your electron density in, you can't donate it, right? You can't be a good Lewis base. So that means out of oxygens and nitrogens, oxygen's the weaker base. More stable, weaker base. More electronegative atom, the more stable it is, the weaker the base it is. Okay, so that means that nitrogen's less stable. It's a stronger base. So this is our strongest base. All right, another thing that stabilized bases, we're not going to go through them all, but another thing, because we have 3 oxygens here. The third thing that stabilized you was resonance. Do any of these Z groups, there's an oxygen here, an oxygen here, an oxygen here. Do any of these Z groups exhibit resonance delocalization of the anion to stabilize that base or to stabilize that charge? The first one, the second one, or the third one? The first one, yes. All of these atoms are oxygen, so they have the same size. None of them is bigger than the other. All of the oxygen atoms that are negative have the same charge. They have the same electronegativity. So one's not more electronegative than the other. But the thing that's different between these 3 oxygen atoms on our Z groups is that the oxygen atom of the anhydride leaving group, our carboxylate, is resonance stabilized. Resonance stabilization makes you a weaker base. It makes you a more stable base. So it turns out that even though oxygen's more electronegative, but smaller than chlorine, it's kind of in the middle, that it turns out that this is a weaker base stabilized by resonance than the other 2, okay? So here we have a basicity trend. Out of our, I'm going to go back a slide just to warn you, okay? Let me go back 2 slides here. Out of all of these main functional groups here, what we've done is we've said, let's look at the Z group next door. So I pulled off all the Z groups, okay? I said, let's look at these Z groups. in order to determine how positive this carbonyl carbon is, okay? How positive it is, okay? So we said if the Z group is more basic, it's able to donate electron density better, then we will exist more in this form, which makes the carbon more neutral. Or less positive. The carbonyl carbon is the electrophile the nucleophile is going to attack, right? When that nucleophile, we've learned this for a few chapters now, when that nucleophile replaces Z, doesn't the nucleophile have to come in and attack this partially positive carbon, open it up, close it up, kick this thing out? Remember that good old, that we'll talk about the mechanism in a little bit, but that's how the substitution occurs. If this carbon is less positive, it's less reactive. And that's where we're going to be headed with this, okay? So we looked at the Z groups, the things attached to the carbonyls. We said if that Z group is a better resonance donor, it's more basic, then we're going to exhibit less positive charge on our carbonyl carbon because 3 will be more prominent, okay? So when we look at the different Z groups, we say our weakest base, the one that doesn't donate hardly any electron density to the carbonyl because it's a bigger atom, so it doesn't get a good overlap, is chlorine. So it's our weakest base. Then the anhydride Z group, called the carboxylate, is the next weakest. Hydroxide and alkoxide, remember how we said that like alkoxides are the organic version of hydroxide? If you replace an H with an R group, you basically have the same thing. They have about the same basicity. They're both strong bases. And then the strongest base in this category is the amide, anion of the amine. So what this means, this base order, is that the amide is the strongest resonance donor. Let's write that. Best resonance donor. That means that the chloride is the least resonance donor, donating. Okay. Just curious, is it easier to remember the conjugate in order to determine the weakest base as well? Yes, you could also do that. Like the stronger the acid, the weaker the base. Yes, you could do that as well. Mm-hmm. And then the Y is because of these 3 trends here, right? Yeah, the more stable the base, the better the leaving group. Exactly. The stronger the base, the worse the leaving group. Yes, and we will, that's something we've learned before too. So it's the best resonance donor. Now, what does this mean? All right, if amide is the best resonance donor, I keep wanting to go back here, okay? This resonance structure then is Z, well, I won't ask a question. Z is bonded more tightly back to the carbonyl. Do you see that? If we look at our hybrid, the better our base is, the stronger the base, the more tightly bound it is to the carbonyl. Now, if you're more tightly bound to the carbonyl because you've got more pi character, right? More double bond character than single bond. This is all single bond. The more tightly you're bound to the carbonyl, the harder it is for that leaving group to leave. True? So we've got to put all this together. But basically, what we're saying here is the basicity of nitrogen, or not nitrogen, the basicity of the Z group. As we're able to donate electron density in, we stabilize the carbonyl group. That's what this is. The stability of the carbonyl increases because we're tightening this bond here. We're pushing electron density in, we're tightening that bond. We're making this compound more stable as our base is stronger and able to resonance donate. So out of all of these Z groups, we now have, I think we've learned this trend before, but we'll learn it again. We have a reactivity order of the carbonyls. If we're going to be doing nucleophilic acyl substitution, how strong your nucleophile is part of the reactivity. How strong your electrophile is, though, is also part of the reactivity. The other thing that's part of the reactivity is how strongly bound your leaving group is to your carbonyl. And the stronger the base, the stronger that atom is bound to your carbonyl, the harder it is for that leaving group to leave. So the reactivity here is that the amides, those were the strongest, strongest bases. That means they're the best resonance donators. That means that this bond is very tight and that amide is very stable. So out of all of our carbonyls, of the carboxylic acid derivatives, the amides are the most stable. Another way to say this is least reactive. All right, and then as we go through, if you have an oxygen, these are greater than, less than signs. Well, I'm going to do it in order of reactivity. So let me go this way. In order of reactivity, the amides are the least reactive, okay? Then we have our esters and carboxylic acids. Because their bases are both strong bases, good bases, they're about equal. The carboxylic acid is about just as reactive as an ester. They have about the same reactivity. Now, what is that reactivity? I'm going to call it mildly reactive. They're mildly reactive. Carboxylic acids and esters are not extremely reactive carbonyls. They're mildly reactive, okay? Then we go to our anhydrides. The anhydride leaving group is a weaker base. This bond is not as tight because the oxygen is not only pushing electron density in toward that carbonyl, it's also pushing electron density in toward its leaving group. So the amount of pi donation toward the reactive carbonyl is less. So this is not a very tight bond. So because of that, anhydrides are more reactive. So I would call them reactive. They're reactive. Anhydrides will react with nucleophiles more readily because this is not as tight of a bond. Okay, and then we get to our acid chlorides. This chlorine was the worst of all the bases attached to the carbonyl, which means it's the worst pi donor, okay, the worst electron donor. So because of that, this is a very weak bond, okay? That means that chloride is going to be a better leaving, it's going to be easier to cleave that as a leaving group. So I would say this would be very reactive. The acid chloride is a very reactive group. Now, that also means it's the least stable of all these carbonyls. The least stable. All right, so I like that some of you are remembering that the leaving group trend, because that is very right. The Z groups, when we do substitutions, they have to be leaving groups. And in order to be a good leaving group, you have to be a weak base, because weak base means non-reactive. So the chloride, being the weakest base, is also going to be the best leaving group. Now, that means most stable on the product side, but on the reactant side, it also means the least bonded. So we're looking at the other side of the picture now. Do you all understand that? Instead of looking at reactants going to products and saying, well, why does that substitution reaction work? Instead of saying, well, because the products are stable. That's the stability aspect, delta G. Delta G, like stable things. We go to a negative delta G. We go downhill. We're also now looking at the reactant side. We're saying how reactive, so not how stable. If this is an energy curve, we're not only saying how low or how stable are the products, we're saying how high or how reactive is the carbonyl. The less bound the Z group, the more reactive the carbonyl. It gets higher and higher. And so the delta, as the carbonyl, let's say from an amide, which is pretty stable, less reactive, stronger bonds, all the way up to an acid chloride, more reactive, that means higher in energy, weaker bonds, okay? As we react these, the delta G toward the products will get lower and lower. Okay, let's say our amide, our leaving group isn't so stable. Its delta G is very small. The delta G here is very big. So there are several aspects to the nucleophilic acyl substitution, why the reactions are going to go, and the reactivity versus stability order of the reactants and the products determine the outcome in kinetics of the reaction. I hope that makes sense. All right, that's our theory part of the chapter. Now let's start talking about nomenclature. Let's take a turn here, okay? So we're going to do nucleophilic acyl substitutions. Different carboxylic acid derivatives have different reactivities. We're seeing the leaving groups, the Z groups, have different basicities that contribute to the reactivity of the carbonyl. Now let's move into naming these compounds. Now we've already learned how to name carboxylic acids, right? That was on the last test. So what we're going to do is to name a carboxylic acid derivative. The reason we call them that is because we are going to name them based off the carboxylic acid name. The carboxylic acid derivatives, that's my abbreviation for that, carboxylic acid derivatives, okay? They're named based off of the carboxylic acid. They're named based off the carboxylic acid. So the first thing we're going to have to do to name all of these different functional groups is to name the compound as if it were a carboxylic acid and then change that name. All right, so that's our precursor. Now, we're going to look at acid chlorides first. I'm sorry, my old book called them acyl chlorides. And so, I mean, they're the same thing basically. So sometimes I say acyl chlorides instead of acid chlorides. Okay, if you have an acid chloride, it can be either cyclic or acyclic. Now, acyclic just means bonded to like the end of a chain, because this will definitely be a chain terminator. Notice there's no R group on this side of the carbonyl. So they will always be chain terminators, just like carboxylic acids were, okay? Now, they can be acyclic or they can be on a ring. Now, because they're chain terminators and there's no R group on the other side, if they're on a ring, they cannot be bound inside the ring. Like that's why we didn't learn about cyclic versions or names of acid chlorides. They have to be bound outside of the ring, just like the carboxylic acids were. Remember how we had an OH group? There's no way that could be part of the ring. It had to be bonded to a ring. So those are the two types of compounds we're going to look at: acyclic and bonded to a ring. So if we're acyclic, what we're going to do is we're going to name as if it were the carboxylic acid, but we're going to change the ic acid of the name to ill chloride. Ic acid to ill chloride. Okay. I'll give an example here. Here's an example of an acyclic acid chloride. Okay. Now, this is acetyl chloride, because if we took this compound and it was the acid, do you remember that you have a CH3 group bonded to a carbonyl? That was an acetyl group, an acetic acid group. This compound's name was acetic acid. Okay. If we take the ic acid off of acetic acid and we put ill chloride on instead, we have acetyl or acetyl chloride, acetyl chloride. So we take the ic acid off, put the ill chloride on. Now, we could name this by IUPAC as well. If we name this compound by IUPAC, it's got 2 carbons, 1, 2. In our previous chapter, we called the acid version of that ethanoic acid. This is IUPAC. If that was ethanoic acid, and it says that if we have an acyclic acid chloride to change the ic acid to ill chloride, we're going to take off the ic and acid, and we're going to add ill chloride to the name. Now, this is where it starts getting weird. It sounds weird at first, but I'm going to show you the whole name. Instead of ethanoic acid, it will be ethanoyl chloride. Ethanoyl chloride. And that sounds weird to people at first. So if you're an oic acid, notice we're keeping the O on. It's only the ic acid that gets changed to the ill chloride. So ethanoic acid is ethanoyl chloride. Propanoic acid would be propanoyl chloride. What's another one? Octanoic acid would be octanoyl chloride. Very strange, right? I think it's strange. But take ic acid off, add ill chloride on. Okay. Now, what if we are bonded to a ring? Now, remember, if you were a carboxylic acid bonded to a ring, like down below here, remember, we would just name the ring, or name the ring, whatever was attached to it, and then at the very end of the name, just add the word carboxylic acid onto the name. So this would have been cyclohexane carboxylic, and then the second word is acid. Cyclohexane carboxylic is one word, and then acid's the other word. Do y'all remember doing that? I know it was before break. Okay, if that was cyclohexane carboxylic acid, we're going to take the carboxylic acid part off and add carbonyl chloride on. Carbonyl chloride. So this will be, it's a big word, cyclohexane carbonyl, I don't know why I'm saying oil. Cyclohexane, that's an E. Okay, cyclohexane carbonyl, and then chloride's a separate word. Cyclohexane carbonyl chloride. Cyclohexane carbonyl chloride. I'm repeating it because if you hear it a few times, it starts to sound natural. One of the best things you can do with nomenclature when you're practicing it is to say it out loud, because you start hearing it, it kind of internalizes. All right, here's another example. This is an open chain, isn't it? So for open chains, we're going to name them just the way we would name the carboxylic acid, but then change it to ill chloride. So let's see here. How many carbons are in the parent chain of this compound? What's the longest carbon chain? Let's do some IUPAC here. Yes, 4. We've got 1, 2, 3, 4. So that'd be butane. And we've got a methyl at carbon 2, right? Now, butane, if it was the acid, it would be butanoic acid, right? So this would be 2-methyl. And I'm going to run out of room here. Now, 2-methylbutane, now it would be oic acid. But we're going to take the ic off, right? And we're going to add the YL on, butanoyl chloride. 2-methyl butanoyl chloride. So we find the longest chain still with our substituent, but it's the ill chloride. All right, that's not too bad, right? Ic acids become ill chlorides. Works in all circumstances. Okay, 2-methylbutanoyl chloride. Let's move on to anhydrides, okay? So if we're going to name anhydrides, remember, once again, we're going to name them as the carboxylic acid. And then we're going to change that name. Now, I'm going to go down to the bottom real quick. This is an aside. Aside means I want to tell you this first. The word anhydride, you've heard that word before. You know what it means. It means without water. Something's anhydrous, like an anhydrous salt. It's a salt without the water bound into the crystalline lattice, right? So anhydride means without water. The reason anhydrides are named anhydrides, they are made from carboxylic acids. So if I take a carboxylic acid and I add in another carboxylic acid, now those carboxylic acids could be the same, okay, or they could be different. Now, if they're different, aren't we mixing two carboxylic acids? If we take one carboxylic acid and we're going to react it with another, this is how we're going to make anhydrides, okay? Anhydrides are made by the loss of water. So if we lose HOH from this molecule, we will make a new molecule. We're going to bind it together as the anhydride. It's the two acids when we mix them without water. So our new compound will be the anhydride. The anhydride is when you mix two carboxylic acids and they lose water when they react. Makes sense. Now, the reason we call, if you have two different R groups, we mentioned this on the first slide, a mixed anhydride, like for example, this one is mixed, instead of calling it unsymmetric, because don't you think unsymmetric sounds good? I think it does. The reason they call it a mixed anhydride instead of unsymmetric anhydride is because you've mixed two different carboxylic acids to make these. So that's how anhydrides are made, well, one main way, and that's how they're kind of named, from the carboxylic acids. This is called dehydration. Yes, it's a dehydration. It could also be called a condensation reaction. Very good. So our mixed carboxylic acids here made our mixed anhydride. Now, if I added two of the same carboxylic acids, I would have gotten the symmetric anhydride out. I just want to mention that because notice how they're made. You can use one carboxylic acid or you can use two different ones, and that'll affect the name of the anhydride. Okay, so that was our aside. So let's go back and learn how to name the anhydrides real quick. Remember, I did mention that we have two types now, and now you know how they're made a little bit. We have the symmetric and we have the mixed. Let's start with symmetric first. Symmetric is when you take the same carboxylic acid, it reacts with itself to form our symmetric anhydride, okay? So if we form a symmetric anhydride, we're going to name it as the carboxylic acid, but then change the word acid only to anhydride. Okay, so here's an example down here. Here we had, if we look at this, we can kind of see what carboxylic acid made it. Ethanoic acid reacted with ethanoic acid. So there's two carbons there. Now, ethanoic acid's more common name that is used is acetic acid. So here we have acetic acid. Because remember, this is an acetyl group, a methyl group next to a carbonyl. So this is acetic acid. Okay, so if we have this compound, and we look at one side, and one side of the symmetric anhydride was acetic acid, and the other side's also acetic acid, it's symmetric, we're just going to call it acetic anhydride. So we take away the acid, and we add the word anhydride. So it's acetic anhydride. The anhydride coming from acetic acid. Okay, what if we have a mixed anhydride? The R groups are different. Here's an example. We have, a carbonyl methyl group on one side. We have a carbonyl benzene on the other side. Those are the two different acids that I'm circling like that. We think about these as the acids that made those compounds. That's how we're going to derive them. So if you have a mixed anhydride, we're going to alphabetize. both of the acids, and then replace the word acid with anhydride. All right, so if this is acetic acid, do you know what the one in blue is called? I'll give you a second. What is this carboxylic acid called? It's got a name. I'm just going to put a circle there because I'm being lazy. Yes, benzoic acid. Very good. Let's write that down. All right. So we've got acetic acid. I guess it was on the screen, darn it. And benzoic acid. Sometimes I don't go through the nomenclature, so that's why I write it on there. I'm like, go through the nomenclature on your own. All right. We've got acetic acid, benzoic acid. When we alphabetize those, we're going to get rid of the acid, put anhydride down, but we're going to just name each carbon chain first. So we've got acetic, benzoic, anhydride in alphabetical order. Acetic, benzoic, instead of acid, anhydride. Does that make sense? So when you look at anhydrides and you try to figure out how to name them, break them down, kind of like I used the circles example, into their original acids. Name the acids, combine those first names alphabetically, and add anhydride at the end. If it's a symmetric anhydride, you don't need to say it twice. You don't say acetic anhydride. You would just say acetic anhydride. It's understood then that it's symmetric. If I named this instead of acetic, if I named it with IUPAC, it would have been ethanoic. So I could have named this also ethanoic anhydride. That would have worked too. All right. I'm just looking at chat and everything. Okay. Let's move on to esters. Okay. Don't think we've named esters yet. Nope, this is the first time. I get deja vu sometimes. I'm like, I think I've been here before, but I have not. Okay, remember what an ester is. An ester is an R group attached to a carbonyl, okay? And then it's got another OR group. I'm going to call that OR prime on the other side. Okay. The OR group attached to the ester is part of the leaving group. This is going to be called the alkyl group. It's an alkyl group. That is a substituent. It is not part of the base name. So when you go to find the longest carbon chain, remember like if you have a carboxylic acid, if this was OH, that's not part of the parent chain. The parent chain was over here, right? Okay. So if there's an R group attached to the oxygen, that's considered a substituent bonded to the chain, except it's bonded to the alkyl group. Okay. The parent chain is on the carbonyl side. So you're going to have the parent chain be on that side. It's the R group attached to the carbonyl. Okay, and we'll talk about how to name it in a second. All right, so what are the rules for naming an ester? For naming an ester, we're going to name the R group bonded to the oxygen as an alkyl group. Okay, that's just what I said. The name of the alkyl group ending in the YL suffix becomes the first part of the ester name. So if that OR group was a methyl, so if it was like OCH3, okay, if it was an OCH3 group, that would be a methyl. That would be the first part of the name. Okay, now the second part of the name is the parent. What we're going to do is we're going to name the acyl group, that carbonyl part, here's your acyl group, as the carboxylic acid, but we're going to take off the ic acid from the parent carboxylic acid, and we're going to add 8 to the end. We're going to add 8 to the end. So instead of well, we'll do an example. Let's say here that I have a butane chain with an OR prime, okay? Well, actually, let's put a methyl group there because we already did the methyl part at the top. So here we've got a methyl group. That is the alkyl group bonded. It's going to be at the front of the name, methyl. Now, when we go to name the parent chain, that's the carbonyl side. This has 4 carbons here. 1, 2, 3, 4. Butane, right? But how would we name that as the acid? Butane would be, if that were an acid, it'd be butanoic acid. Oops. And this is all one word. Oh, actually, it's 2 words. Sorry. These are 2 words. Space. This is where it gets weird. Usually our substituents are part of the word, but not here in the, there's a space here. So it's named like the ionized form. Yes, exactly. It's named kind of like the carboxylate form. Exactly. So we're going to take the oic acid or the ic acid off. And we're going to add 8. And I guess that's a good way to think of it, Claudia. If you had the carboxylic acid, you could think of the R group as being kind of the salt bound to the OR group, you know, except they're legally bound. But you could think of it instead of like the metal, like sodium benzoate, you're thinking of the alkyl version of that ionized carboxylate. You know, I've not thought of that in a while. I guess because I just named them now. It's kind of second nature. But yeah, that's exactly how you're going to name it. So you would name it as the 8. So when I went to name this compound here, for example, in the pink, it would be the methyl, kind of like the sodium cation, sodium something. It would be the methyl butanoate. 2 words. Butano, not ic acid, butanoate. Methyl butanoate. Very good. Let's see if we can name this one. Anybody want to take a stab at this one? Now, this one's a little bit harder. What is our alkyl name here? What is the alkyl name that goes in the front for this one? Yes, T-butyl. Now, you could write the whole thing out. You could say tert-butyl. Or you could just say T-butyl. Okay, that is our R group. Now, how would we name this if it was a carboxylic acid? Think about this. That would be, what would be, that would be cyclohexane carboxylic acid, right? Cyclohexane carboxylic acid. I abbreviated. Y'all type faster than I write. Very good. So we're going to take the ic acid off, right? We take the ic acid on and we put the 8 on. So it would be cyclohexane carboxylate. Yeah. Okay. Oh yeah, I forgot to add that. That's okay. All right. So it would be T-butyl cyclohexane carboxylate. T-butyl cyclohexane carboxylate. 2 words. So there's a space there. All right. It's a big word. When we do the cyclics, they get so big. All right. I'm going to erase. Well, I'll just do this one really quickly here. Here's another example here on the right. It's named for us already, but we'll break it down. We've got the ethyl. So on the oxygen side, there's an R group attached. That's the ethyl group. So it's ethyl. And then on the other side, we could call this ethanoic acid. So it could be ethyl ethanoate. But as you're noticing, a lot of times for these carbonyl groups, if it's a carbonyl with a methyl group attached, organic chemists instead use the acetic acid version. So this would be the acetate, so ethyl acetate. So acetic acid becomes acetate. Acetic acid becomes acetate. So it's ethyl acetate. Has anyone ever heard of ethyl acetate? Anybody ever heard of ethyl acetate? I bet you would know the smell. I bet you would know the smell. Everyone knows that fingernail polish remover, yes, fingernail polish remover is acetone, famous organic solvent. Methyl, carbonyl, methyl, that's acetone, that's the remover. The nail polish has that ethyl acetate in it. Very good. So if you know that smell, it's actually, I like that smell. Ethyl acetate when it's pure, because sometimes there's other solvents in it as well. Guys probably won't know that smell as much, but it's also found in paints. A lot of, nowadays, a lot of paints are not, they're low volatile, so you don't get that as much, but it kind of has that paint type smell. But ethyl acetate has a little sweetness to it when you smell it. So if you ever smell this, you know, this, and I don't know, the paint store and start smelling some solvents or something in the paint thinner section, ethyl acetate has a little bit of sweetness to its smell. I don't know, but it's a very famous solvent. It's a nice polar solvent for organic compounds. Ethyl acetate. There it is, ethyl acetate. Got 2 carbons on one side, 2 carbons on the other. It's the ester form. Okay, let's name some amides now. Okay, for amides, we are going to do a little bit different. If we're going to start with a simple amide, what in the world is a simple amide? If we have an R group attached to a carbonyl, okay, we know that an amide is a nitrogen with either hydrogens or R groups attached to it, okay? Now, a primary amide, we said, only has 1 carbon attached. So a primary amide is an NH2 amide, okay? We're going to start with that, a primary amide, an NH2 amide. The reason that we're going to start with that, it's the simplest, is because there's no alkyl groups to name, okay? The only carbon chain is over here on the carboxylic acid side, okay? That parent chain side. So if you have an amide, it turns out that if you named this as the acid, if it ends in ic acid or oic acid or ilic acid, like ethanoic acid or acetic acid, or benzylic acid. I'll use those as examples here. Then you're going to replace any of the ic acid, oic acid, or ilic acid. This is where it starts getting, you know, interesting, because you're going to have to mix your nomenclatures. Do I keep the O or not? On amides, you don't keep the O, you don't keep the Y, L. We're going to replace all of these different types of endings with the word amide. I always find that amide names sound very boring. There's no flavor to them. It's not like ethanoyl chloride. That has flavor, right? Benzoate of the ester. That has flavor. But benzamide, it's just very dry to me. I don't know the word amide. So we're going to take that off, all right? So for example, here's this compound here, we've got our acetyl group. That was acetic acid before. Okay, now the whole end of that name has the ic acid on it. So we're going to get rid of the ic, we're going to get rid of the acid, and we're going to add the word amide straight to the end instead. So it'll be acid, it's a weird one, amide, acid amide. Now, some people call this acetamide. Some people call it acetamide. You're going to get a lot of people pronouncing this different ways, okay? It's very interesting. So it depends on if they're a biochemist, a biologist, an organic chemist. It depends how they're using it in the sentence or how it came off their tongue. But that's how the word is spelled. Acetamide, acidamide, acidamide, however you want to pronounce it. All right, but we add amide to the end. All right, I call it acetamide. but that's just me. Sometimes I accidentally call it acid amide though. I don't know. Okay, let's look at the next one. We had benzoic acid. That had the oic acid on it. We're going to take off the oic acid. Benzoic acid, take off the oic acid and add amide. So now it's benzamide. Now it's just benzamide. And then if we've got, you know, a carboxylic acid connected to a chain, for instance, like this would be 2-methyl-cyclopentane carboxylic acid that had the ilic acid on it, you would take the ilic acid off and just add amide. So instead of carboxylic acid, you're going to have carboxamide because you're going to take the ilic acid off. Yeah, eye drops. Yes, look it up. It contains the amide structure. Mind blown. Yes. And, you know, when we're face-to-face in class, sometimes I have students bring in like canned goods or like medication, not to share with others, but I say, bring in something from your house that has a list of organic ingredients. And we look at the back and the functional groups are all there. We just don't know some of them actually though, until we get further on. But yeah, after organic 2, you're going to look at the back of bottles and you're like, oh my gosh, this contains an alcohol, which is why it's water soluble, you know, or something like that. All right. Yeah, very cool. Very good. All right. Now, what happens if we replace one of the hydrogens or both hydrogens on the amide with R groups? So we start putting R groups there instead. That would be a secondary amide. We put 2 R groups, that'd be a tertiary amide. So those, once, just like the esters, they're going to be considered alkyl groups. Now, here's the difference. If we put an R group, I'm going to put an R group here on this nitrogen, okay? If we put an R group here, instead of just saying alkyl and then naming the amide, for amides, for any nitrogen compound, we say that the alkyl group is attached to the nitrogen. So this is not just an alkyl, like an ester, it's not just an alkyl group at the beginning of the word. It's actually going to be an N-alkyl. And it's all going to be attached to the main word. So this is an N-alkyl something amide. So there's no, unlike the ester, there's no spaces. We're going to go back to nomenclature. Remember how, like, if I had like here, there's an alkyl group attached to the ring. It was a 2-methyl, and it all blended in. We're just going to use our locant instead of being on the chain. So instead of having a number, our locant is that this alkyl group is bonded to the nitrogen. And it's all going to be one word, so no spaces. So we have an N-alkyl blah-blah-blah amide, okay? Fill in the blah-blah-blah with the rest of the structure. So to name a secondary tertiary amide, just to go over the rules, we're going to name the alkyl groups that are bonded to the nitrogen atom. Use the prefix N to precede the name of each group. So it's an N-alkyl. Now, if we have more than one alkyl group attached, let's say that I have 2 of the same R groups here. Let's say that that's a methyl and this is a methyl, okay? So we have a tertiary. Now that would be a dimethyl, right? You would call this an N dimethyl dialkyl if they were the same. Oops. Instead of like a 2,2 diethyl or 2,2 dimethyl, it would be an N diethyl, N dimethyl, because they were both on the R groups. If the R groups are different, we've got a double prime here. So like one R group is a methyl and one is an ethyl. You'll put them in alphabetical order. They're just substituents. So like an N-ethyl, N-methyl. And then the rest of the word. N-ethyl, N-methyl, parent, amide. Okay, so we're going to name those as substituents. Then we're just going to name the acyl group, you know, the rest of the parent chain with the suffix amide. All right, so let's do a couple. Let's do this one, okay? So first thing I noticed, this is a tertiary amide. because that nitrogen has 1, 2, 3 carbons attached to it. It's a tertiary amide. These two are methyls are attached to the nitrogen. So this would be an N because there's 2 methyls, okay? So we have to say where each of them is attached. So it's an N dimethyl. Now, we did this one up here, right? That would be benzoic acid, but we take away the oic acid and add amide. So it'd be benzamide. There we go. N-dimethylbenzamide, all one word. Okay. What is the classification of this amide? Is it primary, secondary, or tertiary? Yes, Lauren, it is secondary. We've got a carbon here and a carbon here, right? So that's a secondary amide. Okay. Let's see, what is our alkyl group here? Our alkyl group is... Yes, this is a formal group. Very good. Now, what's our alkyl group, though? It's an ethyl. Yes. Okay. Now, I'm going to name this compound 2 different ways because just as Justin brought up, instead of an acetyl group here, remember a methyl here, that's an acetyl group. If we have a hydrogen bound to this, this is called a formal group. And formal group as an acid, if I named that as the acid, that would be formic acid, named after either Latin or Greek for ants. I can never remember. I have so much random knowledge, but that's where they were derived from, extracting from ants. So formic acid. Now, if I want to name this as the amide, so there's a nitrogen there, it's form amide, right? Okay. That's form amide. So we've got an ethyl group. The ethyl group's attached to the nitrogen. So we've got an N-ethyl form amide. An N-ethyl form amide. Because that's a formal group. Now, I could name this a different way. You could go back to counting carbons and using the IUPAC system. How many carbons are in this parent chain here for this acid derivative? How many carbons are in that chain right there? Yes, 1. All right, good. So there's 1 carbon there. It's right here. Now that's methane, right? So that would have been methanoic acid. Now methanoic acid, we could have called this N-ethyl methane and take off the oic acid and add amide down. So it'd be N-ethyl methanamide. That one sounds a little bit weird. It turns out if they're part of the major groups we've learned, the acetyl group, the formal group, then just call them the acetyl or the formal groups. Usually with IUPAC, that's acceptable. It's a known IUPAC name, kind of like benzene. It's not 1,3,5 tricyclo or 1,3,5 cyclohexatriene. I can't even name benzene. We just call it benzene. The same thing's true for a formal group. We know it's methane, but we'll call it a formal group. All right, good. Okay. Is there more practice for nomenclature? We've gone through the major rules, but you know they are going to require practice because the rules have different intricacies, like spacing or what you do when you leave the O, when you take off the O on the different things. So in your book, there are some good nomenclature practices you can do. And I would really encourage you all, go to your Canvas shell, okay, the McGraw-Hill Connect, that's what I meant to say, and go to your, what is that thing called? Smart Book. I've lost everything since spring break. Go to your Smart Book And you don't have to read in the smart book. I think it's a little clutter worthy to be reading in. Like, I like a nice clean page when I study. But what smart book is great for, which is why I've assigned those chapters there, they're not worth any points. You can go straight to practicing problems. And I think that's a great place for you to drill yourself. And nomenclature is one of those things where you can get more drills in. And it will automatically tell you the answer and why you were wrong and all of those good things. And it also gives you practice taking, reading questions and answering questions on a screen, which, you know, that's how we take the exam. So the more practice you get on screen answering problems, you know, pacing yourself, reading the problem completely, writing down the problem, and putting it back into the computer, that's very good practice also for the exams. So if you haven't been practicing on the computer, that might be something you do. You know, my son's about to take his, you know, they take their school tests. I don't know what those things are called, the Florida tests in K through 12. Because I'm from Kentucky, it's called something different. But yes, FCAT, thank you. I was trying to remember what it was called. They practice not only on paper, but they do practice on the computer as well, because they notice when students practice on the same environment the tests are on, that their grades improve. So if you haven't been using SmartBook to practice some problems, I would suggest moving over there and practicing some. It's a good way. It's different, right? It's different. All right, same thing with MCAT, right? You don't want to just practice the MCAT in a book. You want to practice like, or PCAT or your GRE or whatever. You're going to practice that online as well, right? With the software. Practice taking the test. All right. Let's move on. Let's talk about a few physical properties. This is my only slide for carboxylic acid derivatives, because a lot of times, most of our compounds do not hydrogen bond, but there are two compounds that are very notorious for hydrogen bonding. Carboxylic acids and amides. Now, only if the amides are primary or secondary, they have an NH bond. Those compounds for these types of derivatives will hydrogen bond. The carboxylic acids have that polar OH bond, and amides, if they're primary or secondary, have that polar NH bond. Now, you might think that because the OH is more polar than the NH bond, right? Oxygen is more electronegative, that carboxylic acids would be more polar and have higher boiling points, but you would be wrong. Even though the NH bond is not as polar, if you go back, remember that amides, let's see, where can I write this? You know, whenever I make my slides, when it's not on the iPad, there's the space looks so much bigger. Okay, remember that an amide let's just put one hydrogen on it. Who cares what else is there? Is a good electron donor. Remember that nitrogen is a good base? Because that nitrogen is such a good base, we're not only getting the polar effects of the NH, making this compound polar or hydrogen bonding, we're also seeing that there is charge in the molecule. Nitrogen is a better electron donor, we talked about this before, than oxygen. It turns out that amides are more charged because of this. They have more of this Zwitter ion in their total hybrid character. And we know that charge, like salts and things like that, have higher melting points and boiling points. So on top of hydrogen bonding, the amide is also charged. And these are partial charges, but the amide not only has hydrogen bonding, it has partial positive, partial negative charges, more so than the carboxylic acid. So overall, amides are more polar than carboxylic acids are. So not only can they hydrogen bond, here's an example of hydrogen bonding between two amides. The carbonyl of one amide is hydrogen bonding with the NH of the other amide. And so that's where the negative positive charge, that hydrogen bonding exists. Amides turn out to have, out of the whole series, some of the highest melting points and boiling points if you compare similar molecular weights, okay? So if I look at different derivatives of the carboxylic acids, all right? Here's an acid chloride. Here's an ester. Here's a ketone. And here's an amide, okay? It turns out that amides will always have the highest, for similar molecular weights, the primary and secondary amides will always have the highest melting and or boiling points. So if we compare these, the acid chloride here, its molecular weights versus the others, they're all around 72, 73, 74. Chlorine weighs a little bit more, so that's why it's 78. But for the similar molecular weights and polarities of the carbonyl, notice the boiling point is drastically higher. Here, these compounds, the acid chloride, the ester, and the ketone, there's no H bonding. And there's relatively no partial charges because the atoms attached to the carbonyl are not good bases. So they typically have lower boiling points. But if we compare a similar molecular weight, amide, 73 is its molecular weight. The amide has hydrogen bonding, but it also has partial charges due to nitrogen being a good electron donor and the hybrid existing more in the charged state. Does hydrogen bonding also happen with OH? Yes. So carboxylic acids can hydrogen bond, but there was none in this series. But yes, you're right. So out of all of the carboxylic acid derivatives, only the carboxylic acids and amides can hydrogen bond. But then amides also have a better base bound to the carbonyl, which makes them have partial charges, kind of like a salt with full charges. So because of its hydrogen bonding and its partial charges, amides have, in comparison, really high melting points and boiling points. Look at the difference here. The ester version of this molecular weight, you know, it's a polar compound. Its boiling point was 58 degrees Celsius. If we go to the amide version of this compound with hydrogen bonding and some partial charge, it goes from 58 to 213 degrees Celsius, much higher boiling point. So that is the effect of both the hydrogen bonding and the partial charges in the structure. So amides, out of all of them, even carboxylic acids, if you compare carboxylic acid and an amide, the amide will have higher melting boiling points if it can hydrogen bond, and they're the same molecular weight. So I thought that was interesting. Another thing that's interesting about amides, you've seen amides before. Now we talked a little bit about amino acids, right? Because we're talking about the acid version of amino acids, and the basic part, the nitrogen, the C terminus and the N terminus. Well, when you show proteins being formed, we know that proteins form amino acids from the C terminus to the N terminus. So here's an amino acid. Here's amino acid. Do you all ever have like your, you probably haven't been in bio class for a while, but have you all looked at proteins in biology? Any of you all? And how the amino acid chains form? Your amino acid chains. And they go from C terminus to N terminus, like this is a carbonyl. And you called this bond between the different amino acids. You would go back through the structure. Did you all ever have to circle where the amino acids were? Right? Here's an amino acid. Here's an amino acid. I remember doing that in high school. I didn't know what I was doing back then. I was looking for this versus that. And everywhere where the carbonyl met the nitrogen, you called that a peptide bond, right? Y'all know what I'm talking about? You called this thing a peptide bond. All right. In a protein, the peptide bond is an amide functionality. It's an amide. Now, you have these peptide bonds or these amide functionalities repeating along the amino acid chain. We call these repeating peptide or amide bonds in a long structure. We call them polymers if they're a long structure. So we would call this type of polymer a polyamide. Poly means many. And so a polyamide means many amides bound into the backbone of that protein. Many amides. A polyamide structure. And that's what proteins are. Now, think about this. Were amides the most stable or the least stable carbonyls? Do y'all remember? Were amides the most? Yes, they were the most stable carbonyls because the nitrogen bonded back to the carbonyl really well. It was a good base, right? And so that increased the amount of that resonant structure there. So these were very stable. So proteins, we typically know, like if you put a protein into, like, say, a hot water bath, right? Or hit into heat, it will start to unfold, right? The heat will not break the bonds, though, because they are nice and stable. It might break the intermolecular forces, right? But it does not break those bonds. This is a nice stable bond. Just something to think about. So have you seen amides before? Yes, they are found. They are those peptide linkages, sometimes called amide linkages, found in the proteins. All right. And someone else, who mentioned this? Somebody mentioned, was it you, Justin? Drugs, the antibiotics? Yeah, a lot of antibiotics contain the cyclic version of amides. They contain beta-lactams. Now, remember what a beta-lactam is. A lactam is the cyclic version of an amide. Now, there's an extra bond here. Okay, so who knows what's bonded to this? R group. But if you're a beta-lactam, that means you've got an alpha-beta. You've got two carbons between the carbonyl back to the nitrogen. And that's a four-membered ring. What do y'all know about four-membered rings? Are four-membered rings extremely stable? No, they're not. So while amides typically are more stable structures, putting an amide into a four-membered ring actually makes it more reactive because you have angle strain here. A typical amide, this is 120-degree bond angle, okay? But what's the bond angle here in this four-membered ring, roughly? It's going to be about 90 degrees. We're straining that bond. And so can you make an amide more reactive? Yes. A beta-lactam is a more reactive version of an amide because of the angle strain. So in a lot of different drugs, you will see a lot of small rings at active sites. This is the active site in penicillin that interacts with the cellular wall, the nucleophiles on the cellular wall, the OH groups, and opens that amide up. You can learn more about this in biochem or medicinal chem, but it opens that amide up in that reactive ring there in red and causes the drug to become active or to do its work. And so this is penicillin G. You'll see the difference is like what's attached, what R group is attached there. On the side chain, it's a derivative of penicillin. Here's amoxicillin. I love that one. Is that the one that tastes like bubble gum in the pink? Now they give you pills. I'm like, what's this junk? I wanted the pink liquid. I didn't want this pill. That stuff tastes amazing. Everybody knows. But anyway, you've probably seen or heard of amides before. A beta-lactam has more angle strain. It's a more reactive type of amide versus the more stable type seen in, for example, things like proteins, polypeptide chains. All right, well, let's talk about some interesting esters. I love esters. They are one of my favorite functional groups because a lot of them, if they're a low molecular weight, that means they're not very long chains. A lot of them have very interesting smells. They have characteristic odors. Now, most of the odors are very nice. A lot of the odors are going to either be fruity or nutty or floral. Not all of them. Most of them have a fruitier smell, but some of them are just nasty though. There are some nasty ones. So you have to be careful. But a lot of esters, I don't know if it's the shape or what. I've never studied my olfactory system in my nose, and the neurotransmitters and all that stuff. But something about the ester and its functionality gives you a lot of different characteristic smells. So for example, when we're in the lab and we make an ester, you can smell the ester. That's one thing I missed about being in the lab. Like we did esterification reactions, and each student made a different ester out of different carboxylic acids and alcohols. We'll talk about this reaction. And it's one of my favorite because the whole lab smells good. Some people will make isoamyl acetate. They will, this is an isoamyl group, acetate. That is a banana oil smell. It smells so good. It smells like a banana popsicle. Exactly like it, actually. Then you've got your ethyl butanoate. Here's ethyl and butanoate. Okay, that smells like mangoes. So if you like the smell of a mango, a little more pungent there. Pineapples. Some people will make this methyl 2-methylbutanoate. So it's got the isobutyl group over here on the other side. And that's the pineapple odor. There's other ones too, like some people make the peach oil and other things. And then we just all go around and smell each other's products. Waft, obviously. But the whole lab just smells so good and fruity. But esters do have interesting smells. So where can I buy these? So a friend can make candles. Ah, yeah, you can make them if you can get the right ingredients. All you have to do is take a carboxylic acid and take the alcohol, and you combine them with heat. But you have to make sure that you're making a good smelling one because some of them smell nasty. But if you combine the carboxylic acid with the alcohol, which is usually a liquid, it's its own solvent, and you heat the thing in a closed vessel for about 20-30 minutes, you'll make the oil. But then you have to extract it and purify it. Okay. Yes, they're very yummy. Or you could just buy them. That works too. All right. That's what I always do. I like making stuff in the lab, but I'm like, this hasn't gone through all of the proper testing. I think I'm just going to buy it. I have made soaps and stuff before. All right. Vitamin C. Anybody has heard of vitamin C? Absorbic acid. It contains a lot of hydroxyl groups. So a lot of times when we talk about vitamin C, we're interested in the alcohols and the vinyl alcohol version of this, the vitamin C, because that's what's going to make the compound water soluble. If you have this many hydrogen bonding groups for, let's see, 1, 2, 3, 4, 5, 6 carbons, you have 4 hydrogen bonding groups for 6 carbons. Usually, if you only have 1 hydrogen bonding group, it won't be soluble in water. But if you have lots of hydrogen bonding groups, that will make you more and more water soluble. So vitamin C is a water soluble vitamin. That's why you can have as much as you want, as long as you're drinking your water. You won't OD on vitamin C. Hey, that kind of rhymes. You won't OD on vitamin C because, it goes right through your system. It flushes through. It's water soluble. That's the hydrogen bonding there. But vitamin C also has a cyclic ester. What do we call a cyclic ester group? Does anybody remember? Pop quiz. What is a cyclic? Yes, a lactone. So vitamin C is a lactone. I like to get my vitamin C from cherries because I just like cherries. What's your favorite vitamin C source? Anybody got one? I do like the chewables though. Something about a chewable. Yummy. Oranges are good. Lemons are good. I love anything lemon. I like lemon water. But it's like really acidic and like my stomach's tearing up. And I'm like, why did I do that? I just love sour stuff. All right. Has anybody ever heard of cocaine? Hopefully that's not your favorite source of anything. No, never. That's right. The government is not listening though. Cocaine is an extract from cocoa leaves on the plants. And of course, it's an addictive stimulant, so I'd never tell you to ever use this stuff, right? But cocaine has a lot of lactones in it, these cyclic esters. By the way, these are 5-membered rings. Would that be an alpha, beta, or gamma lactone? What are these? Yes, the gamma, alpha, beta, gamma, because a 5-membered ring lactone, there we go, has 3 carbons between, and that's what you find in the vitamin C and you find in the cocoa leaves. There you go. Coca, not cocoa, coca. All right, so those are kind of interesting places you can find esters and lactones. Let's switch topics again, okay? We've gone over quite a bit. We went over some theory about leaving groups, and basicity, and carbonyl stability. Then we went over some nomenclature, we threw out a couple of interesting facts. Let's get down to the reactions now, the nitty-gritty, okay? So the only reaction we're discussing in this whole chapter, pretty much, we're going to veer slightly at the end. You can blame carboxylic acids for that because they're a little weird. But the main reaction we're going to be looking at is the nucleophilic acyl substitution. It's the title of the chapter, okay? And we've seen these substitutions before, so that's the good thing. We're just substituting all the different derivatives with different nucleophiles, okay? All right. Let's go over the general reaction. And sometimes it's not called NAS, but sometimes for short, I just write NAS. So if you ever see me write NAS in this chapter, it's standing for nucleophilic acyl substitution. I'm just being lazy, okay? Okay, let's look at the general reaction. If we've got a carboxylic acid derivative, remember I said we were going to react with either a negative nucleophile or a neutral nucleophile. And the nucleophile will switch places with the Z group, okay, the leaving group. So our leaving group can either be a full anion if we started with a negative nucleophile, okay? But if we started with a neutral nucleophile, the protonated version, then our leaving group will be protonated at the end, okay? So let's practice just predicting, based on this general reaction, let's practice predicting some products here. So here I have an acid chloride, acetyl chloride, acetyl chloride, and we're going to react it with ammonia. Now, ammonia is written weird here. You might see it written later on as NH3, but I'm trying to train you right now. NH3 is neutral, okay? So it's got a lone pair, so it's a nucleophile. But as it reacts, the NH2 will substitute the chlorine. The hydrogen will be part of the byproduct, okay? So you're going to, if you have a neutral nucleophile, you've got to start practicing pulling out one of those hydrogens before you predict the product. So our product here will be NH2, okay? Well, we have acid amide, however you want to call it. Now our byproduct here is going to be HCl. There we go. So that's how we're going to predict that product, okay? Here's another example. Here we have a carboxylic acid. Now we're reacting with methanol. We've got an H plus here. The H plus we'll learn later on, that's acid catalyst. But that cannot be the nucleophile. The nucleophile always has pairs of electrons. So if I notice here that my nucleophile is neutral, I'm going to pull out one of those hydrogens on the nucleophilic atom. That will not be part of the compound that substitutes. So I'm going to switch the OCH3 with the OH, okay? So I'm going to put a phenyl here so I don't run out of room. So we'll have our phenylcarbonyl. And now I'm going to have an OCH3, the methoxy group. So now I've created an ester. Oops, I accidentally got rid of my Cl. There we go. And my byproduct is going to be, what is my byproduct in this reaction? Water, yes. There we go. We normally don't write byproducts, but it's really interesting for these substitutions. A lot of times you'll see that we do it. And And that'll be interesting when we get to some different reagents that are going to neutralize our byproducts. Like, for example, water. Water is pretty neutral. But is HCl very neutral? No, HCl is a strong acid. So if I'm working in the lab and I do this reaction, my reaction, the product mixture is going to be strongly acidic. I'm going to need to neutralize that before I extract my compound. So do you know how, like, when you're in Beyond Labs and you finish your reaction and then you always have to put it back in the set funnel? You put the reaction mixture into the set funnel and you're going to extract. I wouldn't just put water into this extraction. I might put water with weak base, not a strong base because I don't want to deprotonate, but I might put water in with weak base to neutralize that coming out. So the reason I think on these substitutions that we as chemists a lot of times will put the byproduct down is because we're thinking about the fact that a lot of these byproducts, some of them are strong acids. And if you have a strong acid, you'll need to neutralize it. I'm throwing out that right now because you'll see that later, okay? All right, now if it's something like water, yeah, you don't need to neutralize that. That's fine. Okay, what are the nucleophiles I'm going to be looking at in this chapter? Okay, so we already know what these groups are because we went through the carboxylic acids, the esters, the anhydrides, acid chlorides, and amides. I think that was all of them. So we know what these are going to be. What are our nucleophiles going to be? Our nucleophiles are going to be the following. We're either going to have mainly oxygen nucleophiles or nitrogens. Our oxygen nucleophiles are either going to be hydroxide, that's the strong nucleophile version, okay? Or acetate, that's also negative. I'm going to put the negative a little larger here. So those are the negative nucleophiles. We're also going to see some neutral nucleophiles that are oxygen. We're going to either see water or alcohol, the more organic version of water. All right, so those are our oxygen nucleophiles. Hydroxide, water, alcohol, acetate. Now here's the interesting thing. You can kind of figure out what you're going to make. Let's say that we have this random compound and we add an OH there. If we add an OH in as our nucleophile, what functional group will we make as our product? What functional group will our product be if we add OH negative hydroxide in as a nucleophile? What we'll be making? Yeah, we'll be adding OH. So OH will be here. So if OH is there, this is a carboxylic acid. Very good. Okay, so we can make carboxylic acids by reacting something with hydroxide. What if we add water? What is water? It's just the neutral version of hydroxide, right? HOH. If we add water in, aren't we going to also get a carboxylic acid? Because the OH will replace the Z, right? Okay, so our nucleophiles can either be hydroxide or water. Both of those are going to make carboxylic acids, right? So these make carboxylic acids. What will an alcohol make? That's a neutral nucleophile. What functional group will an alcohol make if we put it in here and the reaction works? We have to assume the reaction is going to work because it depends on what this is going to be. We'll see that later. Alcohols will make what? Esters, yep. So this will make the ester. If we add alcohol in as our neutral nucleophile and we react, if the reaction works, we'll make ester. All right, what about the acetate? That had the negative charge. That was a negative nucleophile. If we add the acetate in and replace Z, we will make the what? Yes, we will make the anhydrides. So now what I want you to start seeing, this is kind of how I'm framing it like this. We're not just throwing in random neutral or negative stuff. The point is, we are going to start with one carboxylic acid derivative, and we are going to be making another carboxylic acid derivative. For example, I could start with the acid chloride, and I could make the carboxylic acid. Ooh, I could take one carboxylic acid derivative and make another with these nucleophiles. That's what they're doing. Does that make sense? And I'm making a mess all over my screen. All right. Let's see here. Let's go to the nitrogen nucleophiles. Now, are any of my nitrogen nucleophiles that I'm going to use in this chapter going to be negative? Are any of them negative? Now, they're all going to be neutral, aren't they? These are the nucleophiles we're going to see. If I have a nitrogen nucleophile, it's going to be neutral. We're never going to use the negative ones. Why? Negative nitrogens are really strong bases, and they're not going to do what we want them to do. They're going to react as bases instead of nucleophiles. So I want you to notice these are all neutral. All neutral. Okay, now let's go here. Let's look at the nucleophiles. They're all nitrogen. We know nitrogen gets 3 bonds. So it doesn't matter if we start with NH3, RNH2, or R2NH as our nucleophile that's neutral. Aren't we always going to get an amide in the end? Yes, we're always going to get an amide. The difference is, oh, I don't know why I put 3 bonds on that nitrogen. I only needed to put 2. The hydrogen goes away. But we're always going to make an amide. The substitution of our nucleophile, how many R groups are attached to that amine, determine what type of amide we make. So if we start with an NH3, which is technically HNH2, we're going to be putting an NH2 group here. Now, if we put an NH2 group there, that's going to make a primary amide. Is that what you all were going to say? Someone's typing. I'm sorry. Yes, a primary amide. Now, what if we start with RNH2? Then we're going to put an RH because one of the hydrogens, right, from the neutral goes away. And that will be a secondary amide. All right. And then if we start with R2NH, that hydrogen goes away, right? We end up putting 2 R groups on. Now we are going to do a tertiary amide. So if we start with a secondary amine, we make a tertiary amide. Does that make sense? A secondary amine, 2 R groups attached, makes a tertiary amide. The third R group is the carbonyl. All right, good. So there's also going to be, well, let's see here. Yes, these are all of our nucleophiles that we're going to use in this chapter. Okay, what is the general mechanism? This is important. We've seen this before, but it's always good to repeat. I'm going to use the negative nucleophile first. If we start with our carbonyl with a Z group, okay? Now I'm going to put equilibrium arrows. We'll see why in a little bit. But if I put in my negative nucleophile, okay, the mechanism is how the reaction works. It's not an SN2. Remember, this is an sp2 carbon. You cannot SN2 an sp2. So don't write this down. This is not what's going to happen. I'm not going to attack the nucleophile and the leaving group leaves. That's an SN2 reaction. Substitution in the nucleophile, bimolecular, nope, not going to happen. Because we're an sp2 carbon, the weakest bond always breaks. We have a pi bond. So remember, when the nucleophile attacks the electrophilic carbon, the one with positive charge there, the first thing we do is we open up the carbonyl. Remember this? Okay, so now I've got my nucleophile there. Okay, now that's our tetrahedral intermediate, but we've got 2 electronegative groups here. The driving force is going to be closing the pi bond back up, okay? So we've got a good leaving group if Z is a good leaving group, okay? A weak base. Then we're going to close that carbonyl back up. And now the nucleophile's there, and Z leaves as the anion. Oops, I guess I should have done that, those arrows in red. There we go. So it's a 2-step process. First, we do the addition. And then we do the elimination. We've studied that before, but that's exactly what the mechanism will be. Now, what happens if we have a neutral nucleophile? Okay, I'm going to delete this for the sake of space. You could just write it here if you printed these out, but it's hard on my iPad to do that. I'm going to delete this real quick, okay? Let's put in our neutral nucleophile. It's going to be a little bit different. Okay, so we've got H nucleophile. Instead of hydroxide, this is the water version, for example. Okay, we're going to first attack the carbonyl again. Attack the carbonyl and open it up. We get to that tetrahedral intermediate. Now, for this tetrahedral intermediate, the hydrogen is still on the nucleophile, but it made an extra bond. So now there's a positive charge there. Okay, notice we started with a neutral carbonyl, a neutral nucleophile. Our intermediate needs to be neutral overall. We need to always maintain similar charge. So notice we have the neutral Zwitter ion. There's charges, but it's neutral. Okay, what's going to happen here? Now you can do this one of two ways. I'm going to do it the easy way because it takes less steps, and it really doesn't matter either way. I'm going to do an internal proton transfer. The Z atom, we said, always has a lone pair, right? And so what I'm going to do is I'm going to transfer this proton instead of into the media and back onto Z, which is a two-step process. I'm just going to do an internal proton transfer. Z is going to take the proton off of the nucleophile. So proton transfer is what that's called. So let me label these steps. This is an addition. This is called a proton transfer. Okay. It's going to be our extra step. Now we've got our carbonyl oxygen negative, ZH plus, and our neutral nucleophile. Okay, now we're going to close the carbonyl up and kick our leaving group out. You'll notice it's neutral when it leaves now. Okay, so we're going to close the carbonyl back, kick our leaving group out. This is the elimination step. Elimination. And let's see what we've got here. We closed our carbonyl, driving force of the reaction. Our nucleophile's on there. And we've got HZ is our neutral byproduct. So there's an extra step. There's 3 steps here. Instead of just addition elimination, if it's a neutral nucleophile, you have the proton transfer in between. Okay? Now your book sometimes shows this as, you know, the solvent deprotonates and then the solvent protonates. That's called an intermolecular proton transfer process. What I've done is the intramolecular version, meaning I've just gotten where the molecule does it straight within itself instead of having to go through the solvent. It just depends. They both work. All right, let's move on. When we get to this intermediate here, I want to go back. I already deleted it. Okay. When we get to this reaction, step 1. So here we've got a negative nucleophile. It attacks the carbonyl and opens it up. This is our intermediate, our tetrahedral intermediate. The tetrahedral intermediate, remember I said that this is a reversible process. Depending on how, after addition, we do the elimination. When that carbonyl closes back to reform the carbonyl, if the nucleophile that just added was a better leaving group, meaning a weaker base, the reaction would go backwards and we would actually make starting materials, not products. In order to form product, the leaving group that's already on the molecule, the Z group, must be a weaker base, a better leaving group, in order to drive the reaction forward. When the Z group is a weaker base than the nucleophile, we will form product. that's when the substitution will occur. So we can take a lot of different carboxylic acid derivatives. We can throw in all of those nucleophiles from the previous page. The reaction will not always occur. The reaction only produces product when the Z group is a weaker base than the nucleophile, okay? So here's my weak base trend, okay? Or leaving group ability. Chloride is the best leaving group because it's going to be my weakest base. We talked about that earlier. So if you've got your Z group, you start with an acid chloride. The acid chlorides are the most reactive, not only because the chlorine is not bonded very strongly here, but just like I think Claudia was saying earlier, or maybe Maria, the leaving group is best. So we will form product from that intermediate. So the most reactive carbonyl then is the acid chloride for several reasons, but it forms product from that tetrahedral because chloride's the best leaving group. Okay? Now, our worst leaving group is our strongest base. So if I start with an amide, I have an NH2 group as my Z group, that is the strongest base. This is the worst leaving group. It's the worst leaving group because it's the strongest base, and this is the weakest base. Strong bases are not good byproducts. They are not stable. They're very reactive. Reactive means you would reverse the reaction. So amides are very unreactive. Out of all of the functional groups, amides are the least reactive because they have the worst leaving groups, because that leaving group is tightly bound to the carbonyl. It's the strongest bound, and it's the worst leaving group. Okay, so here's our reactivity. Before we get started in the chapter, anytime you're studying these reactions, because you'll be studying them, I want you to go back to this. If you know this reactivity trend, it doesn't matter what reaction I give you, you're going to be able to predict whether or not the product will form. More reactive compounds, if I throw in a nucleophile and I predict what product I'll make, remember we were talking about that. We said if you throw in some kind of nucleophile, you can predict what type of carboxylic acid derivative you're going to make. More reactive versions of this carbonyl will always produce less reactive. So you're always going to go from more reactive to less reactive, or less stable to more stable is the flip side of that coin. But you're always going to go to a less reactive carbonyl being formed. If you were to form a more reactive carbonyl, that reaction won't occur. You can't make more reactive products. You have to make less reactive products. Okay? So that being said, here's my reactivity trend. The most reactive carbonyl is going to be the carboxyl or the acid chloride. The acid chloride is the most reactive. Then the anhydride, the ester and the acid are about the same, and the amide's the least reactive. So remember we said earlier that this is the least reactive. We said that the acid and ester were mildly reactive. We said that the anhydride was reactive. And then we said that the most reactive was the acid chloride. So that being said, okay, that's a trend we saw on our previous slide. It's just written in reverse order this time, okay? This is the most reactive. If I throw in nucleophiles that will make an anhydride or an ester or a carboxylic acid or an amide, that reaction will work. because you can always go from a more reactive to a less reactive carbonyl. Okay, so if I start with an acid chloride, it will make all of the less reactive carbonyls. Those reactions will work. Okay, now, what if I start with the amide? Can the amide make an anhydride? If I throw in a carboxylate, will that reaction work? Can I go from less reactive to more reactive? No, I cannot go the other way. Generally, we're going to see some tricks, a few. The only compounds that we're going to be able to make are the ester and the acid from the amide, but that's using some magic, black magic. No, I'm just joking. That would be horrible. But you typically, if you're predicting whether a reaction will go or not, it's always a more reactive will always form a less reactive. Those will work. The other ones going uphill, that's a no reaction. I hope that makes sense. All right, so let's go right into the reactions now while we're thinking about that. Here's some previews of our reactions, okay? If we start with, and this is another way to frame what we kind of thought of earlier, and now I'm putting it on paper for you. See, I made you do the work and think about it. Now our book's telling us this. If we start with an acid derivative, so we've got a Z group here, okay? And we put in a nucleophile. Nucleophile can be negative or neutral, okay? We are going to make a new carboxylic acid derivative. Okay? So these nucleophiles that we already talked about will make either the anhydride or the carboxylic acid or the ester or the amide. We defined all of that previously. This is a pretty little chart predicting that. Okay? Now, whether or not these reactions will go depends on whether or not you go from more reactive to less reactive. For example, if I started with an ester, and I want to make the anhydride, well, can I just throw this acetate into the ester and make the anhydride? Claudia says no. She's absolutely right. This will not make the anhydride. That would be a no reaction because we can't make a more reactive carbonyl. Very good. Now, if I started with the acid chloride and added in my acetate nucleophile, could I then make the anhydride? Yes, because I would be going from more reactive to less reactive. That's how these reactions are going to work, all right? So I have a lot of students that miss this concept here. They miss this. This is the big picture. This big picture is going to keep you from memorizing a lot of random reactions. Because if you can understand most reactive usually goes to less reactive, and you also understand the nucleophiles that make these, this is another big one, which nucleophiles make which compounds, you can predict which reactions go. You're going to learn what we call that organic chemistry knack. You know, I'm an organic chemist. I think I mentioned this before. When I'm in the department, people from biochem, micro, biology, genetics, they're coming up to me all the time saying, hey, could you answer this question for me? I'm going to mix these chemicals and I don't want to blow the lab up. Why are they asking me? Because they've had organic chemistry and they know that we don't memorize a whole bunch of reactions. We understand reactivities and trends. And I could have never seen these molecules mixed together in my life, but I'm probably going to do background checks if I haven't. But with a knack, I can tell you probably what's going to happen. Reactivity trends. Organic chemists have that knack. Kind of like a chef in the kitchen versus a cook. The chef has a knack about what tastes good before he even puts it in there, right? All right, let's get to specific reactions now, okay? That's the rest of this chapter is basically specific reactions. Okay. First, I want to mention something. Remember how I mentioned that before, if we have HCl in a reaction mixture, that usually needs to be removed? If your byproduct of your reaction using a neutral nucleophile will produce HCl is the byproduct, then usually we want to form an ammonium salt out of that HCl by putting in a weak base. So when we react, you're going to see pyridine. Pyridine is a weak base. It's benzene. It's a nitrogen substituted benzene. And it's got a lone pair at the bottom here. We call pyridine a proton sponge because it can absorb with this lone pair. It's a weak base. It can absorb protons. And then when it absorbs protons, it produces this pyridinium chloride salt. And that neutralizes the HCl as it comes out. So if you see pyridine in your solution, that's neutralizing the HCl that comes out. So let's just look at these reactions then. Here's our first reaction. These are all reactions, by the way, I guess you start at the top, of acid chlorides. Now, acid chlorides are our most reactive carbonyls. So they're going to form all the other carboxylic derivatives using the nucleophiles. All of these reactions will go because we're going to go from more reactive to less reactive to form the rest. Okay, so let's do our first. Now, I think predicting products is going to be easy now, right? We're going to switch the groups out. If I start with my acid chloride, who cares what the R group is? It could be anything. You're going to look at the functional group. We're organic chemists. We look at reactive sites. We take the acid chloride. We react a carboxylate salt. Now, this could be like a sodium carboxylate, you know, just some counter ions added in. But the carboxylate's the nucleophile. It's negative. We're going to make the anhydride. Now, our byproduct here is going to be chloride. That's a weak base. It does not need to be neutralized, right? It's just a nice weak base because we used a negative nucleophile. Now, our next reaction will be reacting the acid chloride with water. I spelled neutral wrong, but we don't want to add, we do not want to add hydroxide. Is hydroxide a strong base? Yes. Is an acid chloride a reactive carbonyl? Yes. When you were in Gen Chem, what happened if you added a strong acid and a strong base? You created water, but do you remember you created a lot of heat? Do y'all remember those were very exothermic? Exothermic means dangerous, okay? We don't want to create danger in the lab. Acid chlorides are very reactive. So had I had added hydroxide in, which I would never do, reactive plus reactive means a lot of heat generated, exothermic reaction. And that would be very dangerous in the lab. So whenever we react the acid chlorides, we usually try to use weak bases. Now, the carboxylate was a weak base because it was resonance stabilized. That's the only anion we use here. Notice everything else on this page is neutral because we don't want to, everything else, if it was the negative form, would be a strong base, and strong bases would be too exothermic. Okay, so we're going to add the neutral form. Now, because the neutral form, our byproduct could be HCl. So that's a strong acid. We don't want a strongly acidic media because we know that the strong acids protonate the carbonyl. We wouldn't be able to get our neutral compound out very easily, okay? So what we do is we add some pyridine in and we form the pyridinium chloride salt. The HCl's there with the pyridine. It's forming the salt. All right, so let's look at our reaction here. We've got the acid chloride plus water. That's going to make the carboxylic acid. And then I'm just going to write pyridinium chloride because I'm lazy. You can draw it if you want. Pyridinium chloride is our salt. Okay, let's see here. We got the next one. If we want to make an ester is made by adding an alcohol. So if I take the acid chloride and I add in alcohol, not alkoxide, not the negative, just the neutral alcohol. We put in pyridine because we're going to have HCl as a byproduct. Then I'm going to switch my chloride and my OR group, and I'm going to make the ester, which is less reactive as well. And then pyridinium chloride salt is going to be my byproduct, which is up there at the top. All right, so we can make anhydrides, carboxylic acids, esters. We can also make amides. That was the last one on our list. Now, if we want to make amides, we need to use 2 equivalents of our ammonia or the amine, okay? Remember, our amines could either be primary or secondary amines. Okay, why 2 equivalents? We'll get to this in a second on the next slide. But we're going to use 2 equivalents of our nucleophile. One's going to act as a base, the other one's going to act as a nucleophile, okay? So we are going to switch out the chloride with our nitrogen and whatever is attached to it. So we're going to make the amide here. All right, so we make the amide. Now, where does the HCl go? Well, we know amines are weak bases. One equivalent of the amine is the nucleophile. That's what replaced the Z group. The other equivalent of the amine is a weak base, because we know amines are weak base. And acid-base reactions are faster than nucleophile electrophile. So if we only put one equivalent of amine in, we would only get 50% product, because 50% of the compound would make product while the other 50% neutralize the acid. So the reason we put 2 equivalents in is because that weak base, which is our amine, is going to form the ammonium chloride salt. That will have our HCl. It's going to neutralize HCl. So we don't have to add pyridine here like we did with the waters. They weren't weak bases, they were neutral. But when we add the amine in, which is a weak base, kind of like pyridine, half of that amine reacts as base, half of reacts as nucleophile. Does that make sense? So we end up making the amide and the ammonium salt. We protonate the amine with the HCl. All right, good. Okay, here's our mechanisms, okay? Very similar. But first I'm going to do a mechanism with the acetate, because that was a negative nucleophile. And then I'm going to do a mechanism with our neutral nucleophile. And I know we saw the generic mechanisms, but it's always good to review them with real compounds. Okay, so we're going to take the acid chloride, and we're going to react with acetate. Okay, and we're going to do the addition first. So the anion of the acetate, or I guess the carboxylate, opens up that carbonyl. That's our addition step. Oops, got to open up the carbonyl. Oh, negative. And we're going to have Cl, and we have our carboxylate on there. So that's an ugly oxygen. There we go. Okay, so this is our tetrahedral intermediate. It's negative because our nucleophile was negative. Okay, now that's the addition step. Now we eliminate. We're going to kick out the better leaving group. Chloride's the weakest base. Bigger is better, right? It's weaker. So we're going to collapse the carbonyl, kick the chloride out. Now equilibrium, it's going to lie toward the products. That's why this reaction goes, okay? So now we've got the O carbonyl R prime, and our chloride is our byproduct. So we made the anhydride in 2 steps, addition, elimination. Okay, let's do the neutral nucleophile version now. Let's react our acid chloride with water. So I'm going to just go ahead and show the first step here. I'm going to be lazy. So the water is going to oxygen's the nucleophile, attack the carbonyl, and open it up. Okay, and so let's go down here. Equilibrium. We're going to have our open O negative, our tetrahedral intermediate with the chloride there. And then we've added OH. It's positive. Remember how it was neutral? Everything was neutral starting out. So our tetrahedral intermediate now is neutral. It's a Zwitter ion. Do you remember what happens next? We did the addition. Now what do? What happens after the addition? Elimination is not quite yet because we start with a neutral nucleophile. There's something that happens before. We are going to do a proton transfer. Do you remember that with a neutral nucleophile? Yep, the proton transfer. Very good. So I'll put this one in pink. I'm going to do it internally. We know chlorine's got 3 lone pairs. I'm going to use one of those. And look, the proton's so near that chlorine. It's going to pick the proton off, give oxygen its electrons back. We're going to neutralize there. So this is the internal proton transfer. So we haven't kicked anything out yet. We're just making a good leaving group. Because right now, water would be the better leaving group. But if we do an internal proton transfer, now this is the better leaving group, right? HCl would be neutral. Okay, so that's our internal proton transfer. Now we eliminate. So now we're going to collapse the carbonyl, yeah. Close the carbonyl, kick HCl out, right? And that will give us our carboxylic acid plus HCl. Okay, now we've got pyridine in the solution. As soon as that HCl is released, I'm just going to draw the nitrogen benzene lazy man version of pyridine. Pyridine is a weak base. It's a proton sponge. So it is going to neutralize. It's going to pick off that proton and form this salt, the pyridinium salt. Because now that nitrogen's protonated. And so the chloride will cling to it. It'll be the pyridinium salt. So as soon as that HCl gets eliminated, it gets neutralized by the pyridine. Pretty cool, right? Now that's an extra step that we didn't see last time because that's the byproduct being neutralized. It's not the product forming. The product still forms in 3 steps. 1, 2, 3. Addition, proton transfer, elimination. But then that byproduct is neutralized. Neutralization. There you go. Pretty good, right? All right. Let's go to reactions of anhydrides, okay? Now, can anhydrides, let's do this one. If I add Cl minus, like NaCl, my favorite salt, will that reaction go? Here's my Z group. If I take the anhydride and I add chloride salt to it, can I make the acid chloride? No, because the acid chloride is more reactive. If you see this reaction, you're going to write no reaction. That reaction will not occur because anhydrides are more stable. The acid chlorides are more reactive. So that's why you don't see it. You'll see that there's like some reactions you don't see in your book as you kind of study this week. Well, those reactions don't work. Okay, they've already been stated. So we're only showing the reactions that work. Anhydrides, I'm going to go back a bit. Anhydrides can make esters, acids, and amides. Okay, they can make anything less reactive than them. Okay, here we go. So we're going to make the, what are we making here? We're going to take our anhydride. Now, anhydrides, I said, are reactive. Do we want to add negative things to reactive things? Do we want to add strong bases like hydroxide? No, they will generate heat, right? So once again, the reason we're choosing the neutral nucleophile over the strong is the strong base can do some other stuff, but also it's very exothermic, okay? So we're going to add the neutral nucleophile once again. If you're reactive or very reactive, we're going to be adding the neutral base, the neutral nucleophiles instead of the strong bases, okay? All right, So what are we going to be making here? We're going to replace that anhydride leaving group, the carboxylate, with an OH. We're going to be making the carboxylic acid? Yes, and we can totally do that. So I'm going to circle. What I like to do when I'm solving problems is I circle my leaving group, circle my nucleophile, because this might be written as water. Remember, if it's H2O, one of the hydrogens leaves. Okay, so this is an interesting reaction. There's my carboxylic acid. Can somebody tell me what my byproduct is? These are switching places, right? What's my byproduct? Same. Very good. It's also a carboxylic acid. It's H from this. O, carbonyl R. It's another carboxylic acid. How many equivalents of carboxylic acid do we make? 2, right? Now, a lot of times we're going to use symmetric anhydrides so that we don't get 2 different carboxylic acids out, right? If we use different R groups, non-symmetric, we would get 2 different carboxylic acids out. To me as a chemist, that would be very difficult to separate because they both have similar properties, right? So a lot of times we use symmetric anhydrides and then we hydrate them to break them apart. Isn't this the opposite of how we said we made anhydrides? 2 carboxylic acids react together with heat. They dehydrate to form the anhydride. It's the hydration of the anhydride forms the carboxylic acids back out. It's the reverse. All right, so that's good. Now I call that atom economy. I'm getting 2 products for the price of 1 reaction. Double the amount of product. My boss would be happy with that. All right, let's go on. What happens if I take this anhydride, here's my leaving group, and I react with alcohol? If I react with alcohol, I'm going to get the ester, right? Yep, very good. Ester, and then what's my byproduct again? More organics. We've got to write it. It's another acid. I've got 2 organic compounds in the same mixture. Is this going to be a problem? We talked about this before break. Could I separate this mixture? I've got 2 organics. How could I separate this mixture? Do y'all remember we talked about that in the previous chapter? If you have carboxylic acids with neutral organics like an ester or anything else. Yep, that carboxylic acid. You could, to separate the ester and the acid, do an extraction. Yes, make the ion. That's right. The acid-base extraction. If I deprotonate this with, let's say, sodium hydroxide, I make the anion, and that anion then would go to the water layer. The ester would remain in the organic layer. So I could do an extraction. Extract. Acid base. Very good. All right, so it's not a problem. Still not a problem. Okay, let's look at the next one. Now, once again, we're going to have to use 2 equivalents of amine to make the amide. Because one equivalent will react with the acid or the base, okay? As acid or base. The other equivalent will react as nucleophile. So if I react with ammonia, like NH3, the NH2 will substitute. So I can make the amide. And then instead of getting the carboxylic acid out, the carboxylic acid is an acid. If we use 2 equivalents, the other's the base, they will deprotonate each other, right? So I'm going to make the ammonium carboxylate salt. And that ammonium carboxylate salt, it's an organic byproduct, right? It's water soluble. once again, based on solubility, I can extract the amide, which will be in the neutral layer. The salt would go to the water layer if I dumped this reaction mixture in water. But one equivalent acts as base, the other acts as the nucleophile. So that's why I need two equivalents. Anytime we use this amine, you'll see that we need two equivalents because one equivalent will react as nucleophile, the other equivalent acts as base to neutralize. Now, I want you to see your text for this mechanism, all right? So if you want to know how this reaction works, go to your text. And it's kind of like the other one where we put in the pyridine and it deprotonated the HCl. When you have the extra ammonia, it will deprotonate the carboxylic acid. It's the same thing. It's a neutralization. All right, we are out of time for today, right? There are more reactions. We've got to keep moving. You saw that the end of this, a lot of these reactions are going kind of quickly, right? It was the beginning with all the theory that took a little bit longer. What I'm going to do is I'm going to finish about probably a 35-minute recording, if you all don't mind, of the rest of this chapter as a lecture so that you can finish up this chapter this week. We've gone over a lot of the important details, but we do want to go over, I want to go over a couple more details of the reactions a little bit more closely with you. So it is okay if by maybe tonight or tomorrow, you'll see the rest of this lecture appear? I will do that. I will post another lecture by tonight. It will probably, I have another class and some stuff, so it'll probably be later tonight, but I'll get it out there to you. So by tomorrow morning, it should pop up. I'll put it under the lecture module under our chapter so you can find it, okay? All right, but we've gone over a lot of the theory, so a lot of this is going to be very explanatory now. You'll understand a lot more of it. All right, guys, I've got to go to my next class, but you all have a great day. Let me make sure I got everybody on the roll real quick. Ooh, where did I put my roll? Looking, okay, here. Is Darwin here? Is Ryan here? Or Cardi? Cardi, Ryan, Darwin. All right. All right, well, y'all, I've got you, Claudia. You all have a great day, guys, and I will be recording that tonight and putting it up by tomorrow morning. Probably tonight. Bye, guys.